So I would like again to thank you, Dr. Sishar, for the chance to talk at VISTEC, and actually there's quite a few people from TGGS as well listening to the talk. Today I'm going to present some of the work I've done that are related to virtual memory design for modern architecture. When I say modern architecture, what do I mean? Basically, I'm looking at a cloud cluster in modern day. Let's say you Amazon, right? You will be hosting a bunch of machines for clients to use, but these machines in modern day, it gets very heterogeneous. What I mean by that, sometimes you actually allows the client to use the GPU to accelerate applications such as machine learning. You can even, for example, use it to mine Bitcoin if you want, right? So basically, these GPU are really powerful machine that you can utilize. If you program your application in a certain way, it will be a lot faster than the CPU. Another type of this cloud cluster these days is things like function as a service, infrastructure as a service, or just launch a virtual machine or container on the cloud cluster. And it makes the amount of application that are being run on the machine becoming heterogeneous. You have various types of workload, each with different demand, right? So what we ended up with is that there's no one size fit all policy, for example, for a page size on how to actually manage the cluster. So today we talk a little bit about like how should we redesign or modify the current virtual memory, which has been proposed for 10, 20 years actually. It's an old technology. How do we actually apply it for modern day application? I'll first begin with the first part of this talk where we focus on the GPU. GPU in modern system, if you buy a GPU card, for example, this RTX 2080, right? If I buy them, personally, I like playing games, right? So I would buy them to play games. I can use them to play Far Cry 5, like Final Fantasy and Devil May Cry, on all these like really fancy games that have really beautiful graphics. So that's a traditional way of what you use the GPU for. You can use it to render different animation, different piece of really nice graphics. But there's another use for the GPU, even though it's named graphic processing units. The way the graphic processing unit is designed is also allow you to run many scientific applications as well. Why? It just turns out that this scientific application or machine learning application behave in a similar way as graphic applications. So you can actually do visual processing, linear algebra, complex math algorithm, or domain-specific application like CUDNN or TensorRT from NVIDIA library and run it on a GPU. On top of this, with the new type of GPU architecture that came out, for example, the A100 or the Titan X, right? This allows the GPU to run on the cloud. What do I mean by that? It means that if you run GPU on the cloud, it means you have to actually support multiple clients who wants to use the GPU at the same time, right? Then this gives a massive parallelism that allows the GPU to run in parallel across different clients so that all of them can utilize the GPU. But if we want to share the GPU, if we want to basically buy one GPU and allow many clients to share this single piece of hardware, one of the requirements is you need this thing called virtual memory to support the memory protection. Basically, it allows one application to protect itself from the other applications that are running on the hardware from seeing the application data. It would be bad if the machine learning application you're running is seen by other different applications, right? So you need virtual memory support. The problem is when you apply virtual memory in a similar way as the CPU counterparts, you see that you have limited TLB reach and high address translation latency. So this is a typical x86 address translation, which is prevalent in CPU. The figure here shows some modification to the x86 address translation from the CPU world into the GPU. This is a paper proposed in HPCA 2012, which is one of the good, actually it's an awesome baseline for virtual address, basically applying virtual address and virtual memory support for the GPU. Is that a question? Yes. Uh, but if you use this model where you have the private translation look-aside buffer and a shared translation look-aside buffer, if you miss in the TLB, basically when you want to access some piece of data and the translation data from the virtual address into the physical address are not in the TLB, then you have to perform what we call a page walk. The GPU ran directly into two problems. The first problem is the TLB is limited. So you have to limit the TLB reach. It means that only about a few megabytes of data are stored in this TLB structure if you happen to access a lot of data, which is really common in modern workloads, right? You actually ended up missing in the shared TLB and you have to do page walk. The problem with page walk is long. Instead of one memory accesses, if you have to do page walk in the CPU, you have to actually ended up doing 4 memory accesses just to get the address and then one more to get the data. So the overhead is actually about 5 times higher. Problem is if you think outside of the GPU, when you buy these graphic cards, they come with its own memory, right? So at the end of the day, you can run application on the GPU and actually ended up using more memory than the what GPU have. In this day and age, NVIDIA give us what we call unified memory support, right? So UVM allows you to actually manage the data between the CPU memory and the GPU memory through a function called CUDA malloc manage. It would actually move data in and out of this GPU automatically. But what we found through our experiment is like at some point this management failed to deliver desirable performance because the overhead of this is actually pretty high. So I'll first go to the design goal of what we want to actually propose to address the problem. First, we want to make sure we have high GPU performance. We want to basically manage the GPU memory in a way that you can still deliver really high performance. You also want to make sure the overhead of when you are using too much memory, the overhead is not too high, right? I'm gonna first cover the first goal through our work called Mosaic. This is a paper we presented in Micro 2017. And this is a collaboration between myself and VMware Research as well as UT Austin. Uh, so you again look back at the virtual memory design on GPU. You see that there's a bunch of cores. Each core has a private TLB, and then have the shared TLB, right? This is a typical structure everywhere. The CPU also use this similar structure. Then you have the page walk, uh, which basically perform page walk if the translation data is not on the shared TLB. And as I said, there are two big problems, right? Limited TLB reach, high page walk latency, and it just if the data just happen to be on the CPU side, you also have to bring in those data through the interface that is a lot slower because they're physically disconnected. Think of it this way. Let's say you're comparing the amount of time between accessing data on your own machine, on your own hard drive, versus accessing data from a network drive. So that time would be quite big in terms of the difference, right? And there's also a trade-off with different design choices you can apply here. If you want to increase the TB reach, you can increase the size of the page, right? So you can use large page. One page is 4 kilobytes. You can actually end up using 2 megabytes for the page size. It actually increased the TB reach. And this, however, right, this large page, when you have to bring in data from the CPU, instead of bringing 4 kilobytes, you ended up having to bring the whole large page, which means now you have to bring 2 megabytes. What's the difference? Well, the size is 512 times difference. So you ended up having to wait a lot longer if you have to rely on large page. If you use smaller page, then you ended up with a limited TLB reach. Each entry only corresponds to 4 kilobytes. If you have 512 entries, you only ended up with roughly about 2 megabytes of TLB reach. How big is your application on a GPU? Your footprint typically in gigabyte, which means that you're gonna miss a lot in a TLB. Our research goal is can we get the best of both page sizes? And the challenge is this. Let's say you want to truly share the GPU, right? You have two applications running on the GPU. The way you use the GPU memory is called by calling this function CUDA malloc. CUDA malloc means I'm going to allocate, similar to the malloc call in C, but it will be done on the GPU memory side. And with the state-of-the-art implementation, if basically these small boxes correspond to one small page, and this larger box in the row is when you want to combine the small page together into a large page, right? And you have two applications running, the green application and the blue application, and they allocate the memory in the interleaving manner. Application 1 do it first, followed by application 2, followed by application 1 again, and followed by application 2. And let's say I want to apply Linux huge page, which is basically I'm going to combine these pages together if the large page come from the same application. So if you want to coalesce application 1 pages, you can do that on the first large page frame, obviously, right? And you can coalesce application 2 pages, but at the end, you cannot coalesce these 3 things in the middle, right? Unless you are okay with moving the data out and in, which also causes performance overhead. On top of that, this means that there's no guarantee at all. So you actually need to search the entire GPU memory to see, can I coalesce this? Can I coalesce this? Can I coalesce this? So at the end of the day, you need to search such a large range of memory to actually perform coalescing. A much more desirable behavior is actually something like this. If I have two applications running, application 1 would be doing its allocation, but we provide the guarantee. Let's say application 2 wants the data, want to allocate data. You would actually pick another large page frame that doesn't contain application 1's data. So if you stick with this assumption, what you ended up with is a large page frame that consists of only one application. This means that when you call coalescing, you don't have to think. You can just say, hey, this is for application 1, and this is for application 2. You ended up with 5 large pages instead of 2. Right? This allows you to coalesce without actually moving the data. So this is our design goal. At the end of the day, we want high TLB reach through using large page. But we want to be also greedy. We want to make sure we have low demand paging latency. So we actually, when we move data around between the CPU memory and the GPU memory, this is done through small pages. If we use the mix of the page sizes, another goal that we should have is we should have something that's basically transparent to the application. If you ever program something in the GPU before, you will then know that the overhead of that is that you don't want to re-optimize or reprogram these things so many times. So our design should be transparent. We should be able to apply this and from the get-go use it from the application point of view. And here's a quick overview of Mosaic, right? So basically we did modification in the GPU runtime and the hardware. It consists of 3 components: the contiguity from serving, allocation, the in-place coalescer, and the contiguity aware compaction. And I'm gonna explain this through 2 operations that are common in every single program. The first operation is called data allocation. When you call malloc, and in this case, when you call CUDA malloc, when you want to allocate a empty space in GPU memory. Applications say, hey, I want data. I want a space for my data. Basically, it's called CUDA malloc. This gets sent to our allocator, which then talk to the page table, say, hey, give me 3 pages. The page table would actually give the large page frame that are first unallocated, and will provide a soft guarantee that the large page frame contains only from the pages with one single address space. So with this soft guarantee, we are sure, right, except for a few edge cases, for example, when you run out of memory, you will then be able to conserve contiguity within this large page frame. Once this is done, to transfer the data from the CPU memory to the GPU memory, we don't promote the page into large page yet. You actually bring the data from the CPU in the small page granularity. This allows the transfer to be done quickly. Once the data arrive, as I show here, it was done 1 page at a time. Once the data arrive on a GPU, you can start running right away. right? You don't have to wait for the overhead of demand paging on the large page. So when this is done, the next thing you have to figure out is, well, if I want to combine things together, what do we do? So that's a coalescing operation. And in our Mosaic design, we coalesce only on the large page frame that are fully allocated. We'll mark them as coalescible. And if you have a large page frame that looks like this, which is actually partially empty, more pages can go in. We will not mark them as coalescible yet. We are still waiting for more pages to come in. These actually simplify what page can be coalesced, because once you mark them, you can maintain just one single linked list, or just one list. It's a list of large pages. When you mark the page as large page, you put that page in the list and give that list to the in-place coalescer, which sits between the hardware and the GPU runtime. And the key task is it look through that list. If something exists there, promote the page into large page. And the key task is basically simply just upgrade the page inside the page table. So it sends a signal saying, hey, update the page table. In the page table, if you zoom in, there's going to be a level that corresponds to large page, which then point to another level which point to small page. Recall our textbook computer organization back in our undergraduate year, right? You have page table walk. Each page table walk level corresponds to a certain amount of pages. In this case, there's a large page table and small page table. There will be this one bit called the coalesce bit. If it's 0, it means the page is in the small page granularity. If it's 1, which in this case, if you see that something in that list of large page, you just flip that bit into 1. This means that this is now a large page. The benefit is this is application transparent. You don't have to modify anything from your application. Everything will function like normal, right? And data can be accessed using either of the page size. Are there questions again? Sorry, I guess someone forgot to turn off the microphone. But with this, you can access data using either page size. This actually improves the TLB hit rate because there can be small pages in the small TLB. Because this doesn't really move anything, there's no mapping changes, so you don't have to flush. There's no overhead or TLB flush as well. So let's say you finish using the data. The second operation is deallocation. Free in C code, right? So there's an equivalent of free in the GPU CUDA program as well. When you want to deallocate data, application will send the deallocation command to the our compaction aware, contiguity aware compaction component. It will first splinter the page. Let's say you have this large page. You want to deallocate the page, you would first break them into small pages, and then you slowly free up these small pages, right? As you can see here, you ended up with small pages. This is not a large page anymore, which means that if you keep deallocating many large pages, you might end up into the case where you have memory bloat, right? Memory bloat means that you ended up with a lot of large pages that are partially filled, right? So what we do next is we can perform compaction to decrease memory bloat, right? This can happen only when memory is highly fragmented. So in our work, we actually utilize another earlier work that allow you to copy a page of data from one place to another, which means that you can copy this whole page into DRAM command from one location to another. As you can see, it actually free up large pages here. So once you free up the large page, the list of free pages is then updated in the runtime, give it back to the allocator so it knows that, hey, these are large pages that can be allocated in the future. And now I talk about the design. Let me talk through the evaluation. I'm going to show you just one plot, the performance, which is the only thing, or the main thing that we care about in this work, right? How well they perform.
Okay.
Yes?
Sorry, can I ask a question?
Sure, yeah.
In the previous slides, I'm just curious, why do you copy the blue memory to that to top frame? Yeah. Why
That's
don't you?
a great question, actually. The thing is, when you deallocate, you already break down the virtual address contiguity, right? So even though you bring in the new green boxes, There's not contiguous in the virtual address space. So to actually combine them back again, it actually incurs some overhead. So with that room, it's actually okay to bring in any pages because they're gonna have to operate in a small page granularity. The goal here is basically to free up more large page for future data. The reason why this is okay is in GPU application, you don't call malloc 1,000 times. Typically, you would malloc at the beginning of the kernel, you dealloc at the end. So this allocation call doesn't happen too often, but it usually happens in the initialization phase.
I see. Yeah. It makes
sense.
sense.
So it kind of really worked out in the GPU side.
Okay, right. Thank you very much.
Yeah, no, sure, no problem. So in terms of performance, right, we actually evaluate both homogeneous workload setup where we run the same copy of the same application from 1 to 5 copy. Obviously, each copy would have its own address space. And the heterogeneous case where we would mix a bunch of GPU application and run it, right? We show the speed up of the first baseline, the GPU MMU that I showed in the beginning, the baseline with the private TLB, shared TLB, and the page walk cache actually implemented as well. We compare that to Mosaic, and as you can see here, on average, on average across all these workload setup, on the x-axis, the y-axis, I show the speed up. You can see that we actually gain performance on every single category, right? And compared to the ideal TLB, right? Not just that we improve performance consistently, compared to the ideal cases, we perform actually pretty close to the ideal baselines. So on average, we actually perform within 10% of the ideal baseline. So that's the first work that we did that basically improved the GPU virtual address performance to maintain the virtual address inside the GPU. Our second set of work would now tackle the part where, let's say you share the GPU, two clients want to use the GPU and they somehow allocate more than what the GPU memory provides. This is the paper we presented in ASPLOS 2019, which is 2 years ago, when we still can go to a conference and it's not a virtual conference yet, right? So we actually now look at the memory oversubscription problem. If you look at this, right, the GPU has its own memory, the CPU has its own memory. So to actually bring in data around, you can do demand paging, and this is done automatically. The problem is this is actually complicated. If you want to reduce the overhead of bringing the data back and forth, you can hand tune. And anyone who program on a GPU that doesn't rely on like PyTorch or TensorFlow, you would then realize that actually hand tuning is annoying. Basically, you banging your head on the wall many times to get things right. There are two techniques if you want to do hand tune. You can overlap prefetch request with eviction request. This allows the data to transfer through the PCIe or NVLink at a time. When you can do that ahead of time, once the data gets demanded by the GPU application, the data will be already there. You can imagine there's a complication with that. You need to know exactly when to copy the data. Another method is to duplicate read-only data, which will allow read-only data to actually exist on both the CPU and the GPU. It removes the amount of data that has to be transferred. The downside of that, well, you have to manually move the data. And this requires the knowledge of what's happening at any point of time you're running the program, which is almost impossible. On top of it, once you share the GPU, this problem becomes impossible. You can't hand tune because if you are running two virtual machines, there's no way for you to tell, hey, that virtual machine reduced the number of memory that you use. You have no control over the other virtual machine. The hypervisor even also have limited control over what the application inside the virtual machine would demand. So it's actually the big demand for an application transfer mechanism that can manage the data better. And to do this, we actually first look at the application running on a GPU and try to classify them because we found that they are different. So we ended up finding 3 classes of application. If you look at, for example, 3D convolution, you see that on the x-axis here, I see the trend on what page get access over time. And as you can see, there's this predictable trend from lower address to higher address, right? So it's pretty predictable on what page do I need next. This, we call this kind of workload a streaming access that has us actually, even though they touch many pages at any given window of time, they touch only a small set of working of data. Most of the bottleneck in this type of application is basically if I want to kick some data out because I'm done using it, I have to wait for that because the way they're managed in UVM from the GPU nowadays. Another class of application is similar to the first class. There's streaming accesses, but data reuse as well. You can see this go up in the address space and then come back down again, access the same page again, over and over and over, right? So there's definitely data reuse. But in many cases, any active point in time, you're looking at just small range of data. Most of the bottleneck here is because their data reuse is so far apart, you actually end up moving data back and forth several times. Last type of application is our old friend, irregular application. You can't tell anything. The page gets accessed randomly. These can be, for example, graph application, or one of the, as I show here, it attacks basically using multiple pages at any random time, right? So these random access applications actually have large working sets because you need multiple pages at any given time. And the main problem, because it demands so many pages, it tracks each other. It say, hey, I want that data. The data that comes in kicks out the other data that's already in GPU memory because you have limited memory. We call the first type regular application with no data sharing. The second type is regular application with data sharing. And the last application type, irregular application. The first type can be tackled by just trying to hide the eviction latency. On the second type, on top of just hiding eviction latency, you actually want to reduce the amount of data migration. And on the last type, well, you can't do much, but you can reduce the working set size to limit the number of thrashing, right? So as you can see here, you kind of demand 3 different techniques that are needed to mitigate the different sources of the overhead. So our proposal called ETC stands for eviction, throttling, and compression. It's a framework that first consists of the classifier. Basically, we look at each application, we profile them, we basically run them for a little bit, and so basically to see what type of application they are. Then we apply these 3 different techniques. First is proactive eviction. Basically, we will evict pages out of the GPU memory ahead of time to make room for prefetched data that you can bring in order to make sure data arrive at the memory whenever the GPU kernel wants the data. The second technique is called memory-aware throttling. Basically, reduce GPU parallelisms, basically reduce the performance of the GPU a little bit to make sure that you don't have thrashing, to avoid losing so much performance through thrashing. The last technique is called capacity compression, which is basically in-memory compression, which is actually kind of like done in some sense by UVM already. So we utilize that for how we store data inside the GPU memory. And here's the framework. What we found is there's no single technique that works for our application. So we have 3 techniques, right? Proactive eviction, memory-aware throttling, and capacity compression. And we ended up with 3 classes of application. Yes?
Sorry, can I interrupt again?
Yeah, sure.
Sorry, I just curious about the framework. The classification, is it on the fly or?
It's on the fly dynamically. So it's actually simple to do if you look at the trend, because if you just look at the physical page number, right? You see that if for the regular application, you see the physical page number increase in the regular step. So that would allow you to basically differentiate between regular and irregular application. Random access, just like you see no trend. Then for reuse, we can use compile time information to detect if there's any data reused throughout the application phase. Basically, when you compile a kernel, you can try to detect if the data will be used again when you say relaunch the loop iteration or relaunch the kernel. Right? So this allows you to kind of see into like, are there any data reuse? So with those two combined, it allows you to classify application into three different types.
And this happened at like CPU cycles. I mean, the time scale is very, very fast, right?
So these are actually run while you're running this on a GPU. Basically, when you run this application on a GPU, you can check some of the hardware counter. And based on that number, you then can classify the application just by looking at the hardware counter.
I see. So the current hardware can do that detection.
Yeah. So if you have a regular application, you find that memory access can be coalesced pretty often because they touch the same page over and over and over again. So you actually end up coalescing so many of those requests. So if you look at the coalescing factor, if a high coalescing factor exists, it means that it's likely a regular application.
Okay. Thank you very much.
Another random question, I guess.
Yeah, sure.
So how often do we see applications that tend to go through phases? For example, in phase 1, it looks like a regular thing. And then as it goes through phases, it becomes less regular. But then they cycle through.
That's a great question, actually. The thing with GPU kernel is typically they would change the phase when they relaunch. I mean, not relaunch, but they switch the kernel. So each kernel typically has only one characteristics. So it's actually make it much simpler compared to the typical CPU application to predict.
Okay.
Yeah, but in the worst case, if you really want to adapt to phase changes, then you can reprofile. And to reprofile, you can kind of basically configure the profiling phase to be done every certain, like maybe 10,000 or 100,000 cycle, which is actually quite a long time. So it should cover enough granularity to detect phase changes, but not too often that you lose performance gain.
Thank you.
All right, so basically, let's come back to our ETC framework. We have 3 types of application and 3 techniques, right? And as we just showed, there's no single technique that works for all of them. So proactive eviction we apply if you just detect that that's a regular application with no data sharing. If you are the regular application with data sharing, obviously you should do the same thing with no data sharing, but because the working set size is bigger, what you can do is to do capacity compression. This allows you to compress the data, so hopefully the data you're going to reuse fit in the main memory, and it won't get evicted by the page replacement policy. And if you have irregular application, we will first do compression as well as throttling. Throttling basically means I'm going to lower CPU, the GPU performance a little bit, disable some of the GPU core to make sure the amount of data they touch are still within the GPU memory. In terms of performance, we compare our design with the baseline normalized to when you have unlimited memory, which is this 1 bar here. You want to get close to as close to that 1 bar as possible. The baseline, which is not implementing anything, basically is the default GPU application with just prefetching. Basically, you try to prefetch data. This is a common technique used in machine learning libraries like PyTorch and TensorFlow. And as you can see here, it actually loses quite a big performance when you're looking at regular application as well as irregular application, right? When you apply ETC, this 75% means that my working set is only basically is the amount of memory only fits 75% of my working set. I'm going to spill over 25% of my workload to the CPU memory. With ETC, we found that we recovered the performance to about, on average, about 92% of the baseline. And comparing to the 92% of the ideal cases where we have unlimited memory, as well as about like 50% improvement over the baseline. when you are really short on memory, if the memory only fits 50% of the workload, in the baseline, you see that the performance tanks because you ended up transferring so much data back and forth between CPU and the GPU. And with ETC, even though it's not ideal, right? It got close to ideal with the regular application because that's simple. But at the end of the day, it's performed much better, far better than doing nothing. So what we conclude is it's effective at first identifying application type, because if you mischaracterize a stack, you're gonna screw it up and the performance will drop. And we correctly apply the policy to improve performance, right? So that's all about the GPU side. The other side of things I want to talk about today is if you look at cloud cluster, right? On top of running machine learning on the GPU, you can run things on, like, for example, function as a service, which actually have different various type of workload that run on the cloud. And there's no one size fit out, even for the page size. Actually, many previous works that established some overhead with large page in the CPU side. So this work is a work we did in collaboration with VMware Research as well as UT Austin. This is actually presented last October. It's a virtual event because of COVID. It's called PRISM, Architectural Support for Variable-granularity Memory Metadata. Sorry about the tongue-twisting name. I regret that very much when I actually have to talk through my own title. But joking aside, if you look at the big system with huge page, right, you will certainly get benefit from larger TLB reach. But what are the key problems? The first key problem is if you utilize a huge page, you will run into fragmentation and bloat, right? This is the data gathered from this particular paper authored by Yongjin Kwon at OSCI 2016. And the paper is called InGen. It looks into one of the issues that it looks into is what's the fragmentation if I start running, right? If I start running Redis with and without huge page. So if you do not use huge page, you ended up with low fragmentation index once time goes on, which is the solid bar here. But if you enable huge page, which apparently should give good virtual memory performance, but you ended up with super fragmented memory. And after 80 seconds, every page is fragmented, which is bad, right? So that's the first overhead. The second overhead is if you look at the page replacement policy, if you track pages in the large page granularity, you ended up losing information. So over here, the table shows the the amplification of the data when you have 4 kilobyte pages versus 2 megabyte pages. The table is from the paper called Project Peabody, which is presented in HotOS 2019 by Ivan Putu. And the paper shows that, well, if you start using large page, you start losing information. So your policy can get less and less effective. The third thing that you can run into is the promotion and demotion problem. Again, come back to the InGen paper, the OSDI 7016 paper. The paper run 3 different virtual machines. On the y-axis, basically what the paper shows is it's a huge page consumption across 3 machines. And as you can see here, only VM3 gets to somehow promoted into 3,000. Basically now it's 3,000 megabytes. It used 3 gigabytes of huge page, while VM1 and VM2 only have a static number of huge page. So the problem actually stems from what we call fidelity loss from using huge page, right? So what is a fidelity loss problem? Let's assume we use huge page. Let's assume we use 2 megabyte page size. Over here, I show a picture of the Willis Tower in Chicago. So if you've been to Chicago before, this is one of the skyscraper. And let's assume I need to clean windows, right? If I use a small page, I see some windows being dirty. I was like, okay, that window is dirty. So what I would do, I would go and clean that window because I know exactly which window pane is dirty and it's that one. However, if I use large page, unless I have the dirty window, large page can only tell that whole side of the building is dirty, that whole side. So what can I do as a cleaner? I would then have to basically clean everything, right? I basically have to clean the whole site because I lose this information. The reason is because you have metadata bits that allows the hardware to tag pages information. What are these information? How many times the page get access, whether the page is there in the memory or not, whether the page is dirty, which means are they modified or not. And if you tag page information in huge page, these are typically done inside the 2 megabyte page table entry. Inside the 2 megabyte page table entry, if you somehow zoom it in, you see that the 63rd bit to 20th bit is the physical frame number, and there's a metadata bit toward the tail end of my physical, basically page table entry. And with this, GOS would then use the information to manage pages. Linux come in, okay, I ran out of memory, I'm gonna kick this page out. The problem is with 2 megabytes, the replacement policy will be done in the 2 megabyte granularity, right? So this actually be used, this information is used for replacement policy to manage, for example, if you have a hybrid memory, for example, Intel Optane, right, where you have a DRAM and more of a non-volatile memory or even storage class memory. Mapping of where you put data between the fast and slow memory can actually lead to performance difference. So the problem is metadata bits is now coupled to the page size, right? These actually reduce fidelity as the page size increases. Let's say you use 1 gigabyte page size. You ended up making policy on that 1 gigabyte granularity. And it reduced the operating system visibility into information within the page, right? Because sometimes the policy only is trying to be imposed on just a fraction of a page. And the issue with single granularity is as follows. So this plot shows the hotness value. What do I mean by hotness? Hotness means how often do I actually have to access that part of the data. And over here, this is a hotness value across multiple applications that we are testing. The bigger the bar is, the violent plot, it means that that particular range of the large page is hot. And then if you actually look at this, you will see that the hotness value is clustered at some range of your large page, right? So only a small fraction of the huge page are actually hot. You only want to maintain those information because they are getting used a lot, right? But if you tie huge page metadata to the page size, it means that every single page here are hot. Basically, it means that, hey, we can't decide. Everything's here look the same. They are all equally hot. I don't know what to evict. So our goal in PRISM is basically we want to decouple this metadata granularity from the page size. Why? We would like to allow finer grain and variable metadata granularity based on the application demand. And we want to measure this work on systems that would like to utilize huge pages which are applicable to the CPU as well as the GPU, as I show in Mosaic and the ETC paper, right? Huge page is beneficial. And PRISM contains 2 main components. First is what we call the metadata registry and the extension to the page table. The second component is the modification to the current TLB design. So our goal, as a part of our goal here in PRISM, we want to make sure that the modification to the hardware is minimal. And here's the overview and how we can achieve it. Let's say we have a virtual address. This is like basically if you declare a pointer in C. If you declare a pointer in C, you're gonna get a virtual address. The way the x86 machine or basically any CPU translate that virtual address to a location in DRAM is like this. It would go to the CRT register, which is a register that stores the value of the first level page table. It would then use the part of the virtual address as an index into this table, which then point to the next level, which will use the next index that point to the next level. And let's say we want to provide better granularity for the 2 megabyte page range. Right? So what we do in the second level here that correspond to huge page is would extend the page table to have the MRE or metadata registry entry. What is the MRE? The MRE is a 64-bit space that would maintain the access bit and the dirty bits of the smaller pages inside this huge page. This basically allows us to, even though we are operating in a 2 megabyte granularity, it enables you to track information within basically 2 megabytes within the sub 2 megabyte granularity. The way lookup is done is first now you go and access the page table entry, then you extend this link. It would actually point to the correct MRE entry that corresponds to that particular huge page, that particular 2 megabyte page. And what's in the PTE now? Well, as I showed earlier, there's this physical frame number and the metadata bits, right? And there's this unused bit between bit 11 to bit 20th. What we use here is we actually utilize one bit to show that, hey, is the MRE present? If it's present, go look it up. 3 more bits for the granularity of the access and 3 more for dirty bits. And then we still have 2 spare bits that you can use later. Now I talk about this granularity bits, so let me expand into this a little bit. We have the encoding for the MRE. These are 3 bits total, as I showed earlier, which means that you can have different granularity for the metadata ranging from 1 to 32 bit. And here's the encoding. If you see 000, it means that I only have 1 bit granularity. This is a large page. If it's 001, it means I have 2 bits. If it's 101, then I'm gonna have 32 bits. It means that I'm gonna divide the large page into 32 different regions, and each of these bits correspond to that particular region. And now that I explained the change in the page table entry, right? Another component that we have to modify is the TLB, because when you do translation, before you perform the page walk, you would go check the TLB. So the TLB support is extended to have PRISM support. If you look at the L1 TLB, it would have the entry for 4 kilobyte base page and 2 megabyte huge page. In the L2 TLB, typically these are combined into one single entity for both 4 kilobytes and 2 megabytes. We extend the large page TLB entry with the MRE. This allows the TLB to be aware of the granularity bits and the access and dirty bits. And when you have a TLB hit, you better go and check the access or the dirty bits. This allows you to get the correct information without losing it, right? Then you set the access and dirty bit accordingly when you have any modification or access to the data. Upon TLB met, it means I'm going to evict this entry to the page table entry. You have to then update the MRE. So we basically go to the page walk cache and we modify that to enhance the page table walker. This allows you to fetch the corresponding MRE entry so that you can update it. And here's the software interface. Basically, if you want to utilize PRISM, you can call md config, which would basically tie the address with these certain links to the types and the bits that you want to set. This is used similar to mprotect. And here's a case study. We basically extend Mosaic, which is the first work I presented today. We now model metadata bits, the LU page replacement policy, and we track page location between CPU DRAM and GPU DRAM. We model GTX 750 Ti and run 15 different GPU workloads. We found that the demand paging performance actually gets better whenever application demand certain page size. Over here on the y-axis, I show a normalized performance to the ideal 4 kilobyte base page in the red bar here. If you use a 32-bit, which means it's closer to the base page, you see that most of the applications still remain and maintain their performance. And this performance gets dropped in some cases if you start to have lower and lower granularity. Basically, once it becomes 8 bits, you lose performance in SC, stream cluster. And once you use the large page, this problem causes demand paging to evict wrong pages enough that you start seeing performance drop significantly in some of these applications. So what we find is PRISM is effective at providing fidelity information whenever applications demand this fine-grained metadata. So we actually have more results in the paper. For the interest of time, I'm just going to quickly go over some of these results. Basically, we provide the CPU and GPU fidelity information across multiple workloads. We have the area, power, and latency impact of our design, and we actually look at the overall impact of memory bloat. If you're interested, please check out the paper. And here, let me summarize the talk again. Now that I talked about 3 different pieces of work, right? So if you look at modern systems, they are really heterogeneous. It contains multiple types of workload. It requires CPU-like virtual memory support. And the issue is, if you want to provide virtual memory support on a GPU, that turns out to be really, really high overhead. So our observation is, well, if allocation are infrequent, you can utilize huge page. If you want to utilize huge page, then you will then have to deal with the demand paging problem, right? So you can have high memory oversubscription. So our follow-up work looks at applications that utilize the GPU, and we found that they utilize them differently. So the solution is, well, we can classify them based on the type and apply the correct policy in ETC. And now that we are outside of the GPU realm and look at any application in general, you also ended up with multiple workload types, each with various demand. So as you can see on PRISM work, we lose fidelity information if we want to utilize huge page. So our observation is, well, if we have a page table structure, we can extend it to basically help store this lost information. Right? So our solution is basically extend the page table to store fine-grained metadata information. And that's it for the talk today. Thank you so much for coming, join us. I would like to then talk a little bit about some of my current work on this direction that I'm working on. Basically, right now we are working with a student, a PhD student in ETH Zurich on a project called Holocron. Basically, what we're trying to do is, with the metadata information, you want to look beyond the access and dirty bits, right? If you think about the way you program, you have multiple types of data structure, and each data structure demands different policy on how you want to manage the cache, how you want to map them in the main memory, how you want to actually use the data. So we actually figure out how to actually enable this information, allow the programmer to tag the information with data structure type, and then the hardware would use that information to apply the correct policy. This is basically aimed, right now, we submitted to ISCA and slightly rejected based on some of the reviewers' comment. We are addressing some of the concern, and we will resubmit to Micro. We also work on a paper called Utopia, which is another master student at ETH Zurich. Basically, we use another method to allow the faster address translation, not through the TLB, but through another mapping table that allows you to actually go to the right places in the memory. And this is also aimed to be submitted to Micro this year. And another project that we are working on is called Memory Harvester. It's a collaboration between me and professor in Korea from KAIST, UNIST, and Ajo University. Basically, what we do here is, well, if you have a bunch of GPU nowadays, right? If you run application on one of the GPU and it turns out it wants more data than what the GPU have, one thing we can, well, typically what will happen is then you actually rely on the CPU memory, which is much bigger. The problem with that is that's slow. You have neighbor GPU. You buy a large cluster, for example, the A100 at VISTEC, right? It's a huge GPU. Can you actually harvest neighbor GPU memory rather than going back to the CPU memory? So we actually did that, and this paper is now planned to be submitted to OSDI or ASPLOS, depending on when we get the data out. We have most of the data we need for the paper. We just basically right now fine-tuning and hopefully address some of the concerns that we have at the moment. I also would like to talk a little bit about our program at TGGS, because I think it's not many people heard about our program. This is basically a collaborative. By the way, people, do you mind if I talk about this? It's kind of like not the scope of the seminar class, but yeah.
I mean, it's fine. Yeah, sure.
Okay, sure.
Yeah.
All Right. So basically, I would like to talk a little bit about the program here at TGGS. Basically, it's a collaboration between KMUT and RWTH Aachen in Germany. We do have double degree, and basically what we want to do is promote traditional research and industry collaboration. If you heard of CMKL, which is a collaboration between CMU and King Mongkut University of Technology Lagerbank, this is something similar, but we actually established way before them. And we offer only master and PhD degree. Also, part of the reason why you might not have heard of it, because it's only master and PhD. And this is actually, once you take class with us, this is count under the European Credit Transfer Accumulation System, or ECTS, which means that this applies to university in Europe. We actually have multiple scholarship for students that want to apply to MS or PhD, and we are industry oriented. We aim to make sure whatever we do would be relevant to the industry. For example, the research I do would be working with, say, for example, VMware. There's a project right now that I collaborate with university in Hong Kong that works with Huawei, right? So we actually would like to do something that have impact to the industry. And students are required to work closely with the industry. There's internship requirement actually for master program. We also have the work integrated program will be opening up soon. Basically, we're trying to like beat out some of the little details to make sure these can be open. A little bit about myself, if you're not would like to hear more from me. I got a PhD from CMU, a master, bachelor from basically I did like PhD and bachelor in CMU. My research area is computer architecture, which basically, if you want to wrap it up, I design computer and their hardware and system software, right? And can link them together. And I right now manage the architecture research group at TGS. And right now we are, me personally, I only have 16 papers to the world best computer architecture venues. Basically, now that this is a network seminar, right? These venues are the same as NSDI and SIGCOMM. Basically, that's probably the easiest way to compare, right? I have 16 of those. The research paper alone that I published now put KMUT and be at the 9th best school in architecture in Asia, as you can see here, and definitely the best in Thailand. And we are actually 64th best in architecture worldwide, better at RWTH Aachen, actually. We have active collaboration with top industry research group and academic labs. And here's some of the research work I'm doing now. I've looked into how to design virtual memory, as I showed earlier. Right? I look at GPU design. I look at DRAM design. These things is basically the top conference in my field. I also look into network on chip. This is basically the topic that I thought would be my PhD thesis, but I shift to GPU because I guess I play too many games. And then I get to actually work with another students that look into how to design DNA sequencing accelerators that kind of like get me interested into designing hardware for bioinformatics application as well. Other works that I've done, I look into file and storage systems with another professor at City University of Hong Kong. If that name sounds familiar, your dean, Dr. Sarana, actually was a professor over there before he moved to VISTEC. I work with Professor Jason Su at City U Hong Kong and the Huawei mobile team. We had one paper already at VISTEC ATC, and we have actually several more projects coming up to be submitted and hopefully accepted to these conferences. And some of the current projects that I'm doing personally here is I look at virtual memory, GPU architecture design. I look at IoT architecture design. For example, Norwich, my PhD students at my lab is actually looking at how to make RPC call faster for many, many modern applications. We look at emerging processor technology, for example, these monolithic 3D chips, which allow everything to be combined in this one single giant chip, including CPU and memory. We look at containerization, how to make Docker, for example, a lot faster. Virtualization, how to make a better virtual machines and cloud infrastructure, which is an area that I would call out that we are lacking in expert in Thailand. We look at system design for IoT, cloud, or self-driving car. I'm talking to another a group of professors from TGS again, but from the more like a mechanical engineering part to talk about, hey, can we have a sandbox for students to play around and like look at self-driving car, because we do have a campus in Prajinburi, and that campus is pretty available as a sandbox. We can kind of like try and experiment something over there, and hopefully don't hit anyone or don't hit any human being. I look into hardware security as well, and also mobile application, how to design a reliable and fast storage systems. So I have a chance to work with Dr. Pat, which is the expert in HPC at NECTEC and Thai Supercomputing Center on high performance graph acceleration, as well as I do collaborate with actually my wife. She's a professor at Chulalongkorn University Medical School, and we are talking about a few projects that we can collaborate over related to bioinformatics. And here's the QR code from my website. So that's it for the talk. I'm sorry for taking 3 more minutes than allocated time. Anyone have any questions that I can answer?
I want to ask about your current work, the 3D modeled chip. When you design the chip, do you consider how to handle the heat, or just make it fastest as is possible?
That's a great question, right? So one thing, well, actually, this is a story that I would tell. I'll start from like my advisor opinion, which is, I think, correct, right? Basically, he said that the art of architecture is all about trade-off. It's all about making the right trade-off for the user side, right? We see user as every programmer, right? When I talk to user, I'm not talking about the client, I'm talking about the programmer, whoever wants to use the hardware. And heat is a big problem in architecture. How do we dissipate the heat, right? One thing that we always try to do is we would first check the budget. Typically, for example, if you want to design a mobile chip, right, you have a guideline. This is similar to architect in real life, right? You would, like, let's say you want to design a house. You would then look at different guidelines, like don't build the house that way or it will collapse. Right? If you build the house that way, it would be like this room would be too hot, right? So a good architect would then check with all these guidelines on how to maintain the correct amount of heat and what to do if it somehow heat up beyond the level that's safe, right? You don't want the chip to actually melt, or you don't want to make a mobile phone that can fry eggs, even though you see some video of that, right? At the end of the day, that's not something you want to do. So heat is a big problem. And performance generally leads to more heat, also more power consumption. So that's a big trade-off to consider. And yes, it's a big thing that you need to figure out. Like, if you come up with a design, you push the boundary, you gain performance. How much heat does it generate? What's the storage overhead does it require? What's the cost overhead of that? So if you read architecture paper, typically there'll be this section called hardware overhead that would discuss like, okay, if I want to implement all these cool new things, how much of the overhead you have to actually pay to get that, and does it worth the performance? So hopefully, does it answer your questions?
Yes, thank you.
All right, any other questions? And by the way, yes.
Yeah. If feel free to ask. This is a very rare opportunities that we have Dr. Rashata with us. So actually, he joined us
next week too. So if you have follow-up questions, feel free to contact me afterward. Or I mean, I like giving. I mean, I like talking. That sounds kind of bad, but yeah, I do like giving talks and explaining what I do. One quick thing I want to clear things up over here. You see different color here, right? I know this is like not a good way to make slides, but these different color here specify one area, like one sub area in computer science. The blue one is architecture. The green one is like more like architecture and system. the red one is like storage system and mobile application, and the yellow one is more like a HPC, and the pink one is more the bioinformatics side, right? So in case for those who join and like, hey, I thought I heard that you shouldn't use a lot of color. Yep, that's what the color is for, specifically for this particular site. Anyway.
So I just have a very general questions about computer architecture.
Yeah.
So just curious, what is going to be like? What is the current direction of computer architecture? What is the trends, and what are the topics that we should look at it?
Oh. All right. So that's a really great open-end question. So let me kind of address it based on each of the sub area that are active right now, right? Obviously, machine learning is getting, well, it has been popular in architecture, basically how to design a hardware for machine learning. These days, making things more flexible, making things more general is one part of that. So it's kind of like the red herring. I can't not talk about it, right? But from the core architecture side of things, right, one of the issues that start to creep up to us is, for example, container. A lot of people use it, right, to run things in the cloud. And if there's actually a paper from, I think 2018 and 19, actually there's multiple papers that talk about this, but if you run container in the cloud, the way it behaves, because if you use function as a service, you only run one function. A lot of the hardware tricks that we do underneath your CPU is designed for a whole application, not just one function. So by the time you gain some history and almost about to apply the correct policy, the function is over. Yay, I'm done. Right? So some of these lead to performance loss. And how would you actually go work through and actually can you provide hints from the software side? Me and my colleague at Zurich has been trying to push toward like, hey, if you use data structure from the software side, right, you actually spend effort to program that. You should find a way to interface and provide that information to the hardware, saying, hey, that's a tree, that's a linked list, that's an array. So we can apply the correct thing rather than trying to understand the trend by profiling and then do the correct thing, right? So these, if you can do it in dynamically when you run it, it can potentially, right, lead to better performance. New type of device always will come up. For example, 5 or 6 years ago, we've been looking in non-volatile memory, like how to do phase change memory, how to design, how to architect them. These days, you're looking at a hybrid devices, like something like Intel Optane, for example. How would you actually write the system software to manage the Optane better? How would you design the memory to provide more bandwidth, to provide more performance? Memory is always another classic topic, but I might be biased because the group I was at when I was a PhD student, we kind of like the memory group in the world, right? So my advisor, Ona Mutlu, is like the memory guy. And we actually do a lot of like frontier work on that front. In fact, our his group, Owner Mutlu group, is actually the one that discovered this problem called row hammer, which kind of opened up another security problem. Basically, you can kind of access one part of your DRAM and will flip the bit on the adjacent cell, right? And I think integrating system design, system software to architecture is big as well. For example, if you look at this aggregated memory, it's like Lego OS, which actually got the, I think, Best Paper Award a few years back, right? Lego OS also like think about how to actually think of memory-centric thing. Memory, at the end of the day, turns into this interface between processing side. If you integrate more and more type of processors like a CPU, GPU, ML accelerators, the DSP accelerators, camera inputs, network interface card, they all sync to memory. So how would you actually design something that's more memory-centric rather than CPU-centric or OS-centric, right? Can the OS be actually think about, hey, that's our interface? Another, I guess, trendy topic in architecture right now is what we call processing in memory. Again, similar to ML, I cannot not talk about it. Basically, processing in memory, once you can do 3D stacking basically means you stack chip on top of each other. The lowest layer can be logic layer. Logic layer means that you can implement some basic processor on there. This can reduce the amount of data transfer between CPU and your memory, right? So if you have a simple operation like matrix multiply, in fact, for example, the DNA sequencing accelerators also relied on the logic layer to compute certain things. If you do that, there's also another overhead of like, okay, you run something on the CPU. It means that the data has to be coherent, right? If you do updates on that logic layer to the DRAM, should the CPU be able to see the updates and how? Right? So these things will always shift the research in architecture. And as we discussed before this meeting, like chiplet, for example, I have a gut feeling that chiplet would also become another major thing in architecture. Which means that you can see the emergence of network on chip again. But this doesn't connect the L2 and L1 anymore. It actually connects the CPU elements inside the same silicon, right? So that's kind of like some of the things that I feel can be important going forward. But I may be wrong. I'm just one researcher, I guess. But these are some of the things that I'm kind of excited about. And one thing that I love, I guess my advisor loves telling his students, and I think it's true again, is also like, this is also an exciting time to be architecture. Like it's kind of like, to me, it's better than back in the day when CPU get faster, it means that you have more gigahertz, like Pentium 1, Pentium 2, Pentium 3, Pentium 4, right? Single core higher gigahertz. These days, it comes in all shape and form, depending on the application. So you can kind of propose new design, propose interesting designs. So it's kind of exciting to me.
Yes. Yeah, I think when you talk about the disaggregate memories and that research direction, it also relates somehow to disaggregate data center networks. That basically you have a pool of memory, pool of CPU, and then you connect them using a very high bandwidth and low latency networks.
Right.
And basically just make a data center network looks like a big giant computer instead of just a small, many of the small computers.
Right. And
the idea
this
can
direction,
be used.
yeah, I agree. And the reason I kind of like it is I like the high level concept, right? I'm sure we all like, hey, that would be good. The main other big issue is how do we engineer that?
Yeah.
It's complicated. That's really complicated to get the cost down to the point that we can actually use it. Like Lego OS, for example, is like one of the good examples. How do you engineer this disaggregated memory, right? So yeah, this is another great example.
Yeah. Yes. It's really nice to have you give a talk today. Okay.